Okay, so in the previous lecture I talked about how to make short pulses by adding many longitudinal modes together, and also by paying attention that they're actually phase stabilized using this satchel absorber device. But actually for the race to the shortest and shortest pulse possible, the key element was really not the satchel absorber itself, since nature provides that for free, it's a curve length, but the key was really to compensate the dispersion to a high degree. So why would I care about dispersion compensation? Well, here is the situation. This is good, all lined up, get a short pulse. Well, I have a little chunk out here because I have only 5 modes. In real life, I have 2 million modes, so there is no chunk here. But if this thing goes through some dispersion, what happens is that the phase between these will start to shift, and you see, even this small shift from here to here, the pulse is nearly gone, because now suddenly I get only a partial constructive interference here, and instead of having nice destructive interference over here, I still have some interference, some constructive interference going on here. If I shift it a little bit more, all I get is noise. I don't like noise, so this is bad. So I care about dispersion compensation. Now here is the typical femtosecond laser. This was one we made in the 90s. The laser is about 1.5 meters long, so it takes the light about 10 nanoseconds to go once around, meaning it goes about 100 million times around per second. Every time it goes through this material here, every time it suffers a little bit of shift due to the dispersion, and the pulse gets a little bit longer. And so what I really need to get such a short pulse, I need a very good dispersion compensation. And this was kind of the Cold War area in the end of the 90s, where everybody was very secretive about how to make the dispersion compensation work. And of course, I'm the friends, I will tell you all the secret details now. So here is a dispersion compensating prism sequence as it was used until actually quite recently still. If you buy a commercial laser, it might still contain something like this, even though I think it's a bad thing. But anyway, so here is the second order dispersion. That's the thing that's bad. This one we want to have 0 across the whole laser. The first order dispersion we don't care, but this one is really the one we want to be flat. Units are funny, femtosecond square, but it comes because this is the second derivative of the spectral phase over the frequency. So 4 millimeters of titanium sapphire, that's about the length we used in the beginning. That's the dispersion a 4 millimeter crystal has. So if I have a 10 femtosecond pulse going through 4 millimeter crystal, it will be already about 40 femtosecond long. So it's bad. I have to do something about that. And so if I look at the dispersion I can get from different materials, prism materials, for instance calcium fluoride or silica, I can play with the distance between the prisms and with the insertion, how much material I actually add. All I can do is curves that look like this. This is calcium fluoride, that's actually as good as it gets pretty much. Or then with silica, if I pull them very far apart, I get this dispersion curve. If I insert it a lot, I get some dispersion from the material. But none of these curves really looks like that. And that's what I need, because that plus that is 0. But none of these really gives me 0. All I can do is I can make it be 0 at one point, but not across a large wavelength range. This is fine for 10 femtoseconds, but it's definitely not fine for 5 femtoseconds. So the problems actually scale to the square of the pulse duration. If I have 100 femtoseconds or 10, 10 is 100 times harder. If I have 30 or 3, 3 is 100 times harder. And so on. So here is the gain curve of titanium sapphire. You see it's really broad. That's actually visible, 600 nanometers. It's nice red. And then this is the near infrared range telecoms around over here. And actually titanium sapphire provides a very large gain bandwidth, but gain alone is not good enough. What I really need is spectrum with a flat dispersion across the whole spectrum. So 10 femtoseconds I require about this spectrum. It's 4 optical cycles. 2 cycle pulse, about 5.4 femtoseconds. I already need to cover spectrum essentially from about 600 nanometers to 1 micron. So that's already a really broadband laser. If your frequency double that, it covers the whole visual range. It's just white light. And if I want 1 octave, that's kind of interesting for optical comp generation, I need much more spectrum. And single cycle is just ridiculously broad. I mean, this is already hard from the gain, but of course, again, our friend Chi3 actually provides enough gain for such a broad spectrum, but it's nearly impossible to compensate the dispersion. Okay, so here is a list of mirrors, how the, nice flickering going on here. A black stack, that's a standard optics. It's known for a long time. It was not easy to make until about the 80s or so, but nowadays it's really easy to make these. The thicknesses of these layers are typically about 100 to 200 nanometers. Optical thickness is a quarter of a wavelength. And so the way it works is constructive interference in the reflected direction and destructive interference in transmission. And since all the layers have the same thickness or optical thickness, it works very well for one color. It doesn't work very well for many other colors. And so an idea was to do a chirped mirror, so I can design the point where the light gets reflected. See, here I have a black stack, but with much shorter periodicity than over here. Well, that's good, because now I get reflection of blue light at the surface of the mirror, and I get reflection of the red light much deeper inside of the structure, so I can actually delay the red respect to the blue, and that's what I want to do, because if blue and red goes through the crystal, laser crystal, blue will go a little bit slower than red. And so if I have a short pulse, they are together, they propagate, so it gets a little bit delayed. Now this hits this mirror, they get restored. And I can repeat that as many times as I want, and I can always maintain, after a full round trip, I can maintain my short pulse. Now that doesn't work, because the problem is that actually the red light gets a little bit reflected here. You know, if you have a piece of glass like at the door, you have a few % reflection, and unfortunately that happens here as well. And so the real breakthrough came with a structure that looks a little bit similar like this, but what we do is we do an impedance matching. So now how stupid is that? I take a mirror, I want 100% reflectivity, and now I put something on top that's an anti-reflection coating. Now that sounds really stupid. But what I do with this anti-reflection coating is I eliminate the surface reflection. And that was really the key idea of getting octave spanning lasers to work. And so this was introduced in the first paper in 1997 and used ever since. And another thing we do is actually turn on the refractive index of the high mediums, like titanium dioxide. It's very thin in the beginning. Here it was a quarter wave, here it's much thinner than a quarter wave. And that also kind of lets me tune slowly the refractive index from whatever I have here, the low index, to the actual high index. This is actually well known from radar technology earlier, after the war, maybe in the 50s or 60s. People already noticed they can make antennas that work this way. Our problem is that these layers are typically only 10 nanometers thick. If I make it 9 or 11 thick, it's already very bad. And so it's very hard to make those mirrors. So here kind of the properties of a normal black stack, you know, the center frequency gets high reflection, and then I get a certain stop band in which all the colors get reflected. For titanium dioxide, silicon dioxide, I get high reflectivity essentially over about 200 so nanometers. The dispersion, I have no influence over it. It has no group delay dispersion in the center, but as I go away, it has some group delay dispersion. And you remember the sapphire crystal also had the same slope, so it's actually bad that I'm left with some dispersion. So here is kind of an interesting plot. This is really the mirror structure in space. So I plot the mirror structure in space here. So just parallel, this is the front surface, then this is the first layer and so on. I shine light on, and it gets reflected very early on in the structure. So here I have no electromagnetic field. Bright means I have electromagnetic field out here. This is for different colors. So all colors in this mirror get reflected pretty much at the same place. That's why it has a pretty flat dispersion. So check it out. Here is the group delay. How many femtoseconds it took the light from here to come back out. And essentially it's a single optical cycle. The light comes out of the structure for all colors. Okay, in the edge, it's slightly delayed. It takes maybe 3 optical cycles into the structure at the edge of my reflectivity band. And so you can see at the very edge here is a little bit bright light coming but essentially all the colors get reflected at the same place. So I don't get this nice delay effect between the different colors. Okay, here is a jerked mirror, and here you can actually design where the colors get reflected. The problem with this is really the surface reflection. I don't want to bother you with the dispersion detail, but instead of getting a nice flat dispersion, I get these wild oscillations that are actually caused by an interference between this light and this pass here. And so this totally is a showstopper, a party pooper as you wish, and I'll have to get rid of those oscillations. And so that's where the impedance matching comes in. Okay, so here we can do the impedance matching in 2 steps. Essentially, we put an air coating on the mirror, which again sounds stupid, but it really helps. But then we have also a few layers that are much, much thinner than a wavelength. And essentially, if you have something much thinner than a wavelength, it's really not there for the light. And so if I make it thin, and gradually thicker and thicker, the light feels, oh, I'm not going through a high-index material, until it's too late and it gets reflected exactly at the right place in the mirror structure. So you kind of cheat the light into the reason it's still propagating in the same low-index material. And so that really works very well. And you see now the oscillations are entirely gone. This is just from analytical calculation. What's really hard is to make it work over very large bandwidth and actually use supercomputers even to optimize such structures afterwards. It's a very highly dimensional problem to optimize. And so here again, the same plot as before, and you can see now blue light gets reflected early on in the structure, so it's not delayed very much. But then the long wavelengths by design, so this is kind of the place where we want everything to be reflected. So the long wavelengths really propagates from here to here and back, and so it has a delay due to this geometry. It really penetrates into the mirror. And so this allows you to design the dispersion the way you want. Here is actually kind of the structure after some initial guess. So air coating, here is the kind of physical thickness of the mirror's material, and here is the layer number as you go through the mirror. So typical jerked mirrors have about 60 layers or so. And here is the interface to air, so the light will shine in and get reflected at a certain position. You can see that actually the layers get thicker and thicker into the mirror because we want the red light to be reflected here. So here I have a black condition where the red light gets reflected in here, very deep inside. And here I have shorter wavelengths, so my blue light gets reflected already here. And here is again this trick where we cheat the photons into believing that they are actually propagating only in low-index material. But you see that actually these thicknesses are ridiculously small. It's only about 10 atom layers. And so that's kind of the hard part to make those things work. So here is kind of a reflectivity curve already. It improved in bandwidth. You remember for the black mirror we had essentially bandwidth going from about 700 to 900. Now suddenly we doubled the bandwidth. And in addition, we could design our dispersion curve to look the way it should look. Unfortunately, there are some residual oscillations, but nevertheless it kind of worked for the first step. Now for an octave, things get a little bit harder because for an octave we really need the mirror to reflect from 0.6 microns to 1.2 microns. So full octave means this is half the frequency of this. And so that's a little bit harder. So our first mirror designs in the 90s, end of 90s, they had dispersion curves like this. This is the dispersion curve of the crystal and the prism sequence. So we want to make something like this green curve. If I add these two together, I get this flat line here. And you can see that the blue curve actually pretty closely approximates that, except that it actually has not quite enough bandwidth to get an octave of spectrum. Plus these oscillations might be a little bit bothersome as well. So if I want more bandwidth, here is for instance a design that has high reflectivity or a little bit more, I get more and more of these oscillations, essentially because it's really hard to get an anti-reflection coating to work over very large bandwidth. And there was some Russian group who actually came up with an analytical expression which tells us it is impossible to get infinite bandwidth of a low reflection air coating. So we will always have problems that at least at the places where this anti-reflection coating does no longer work, we get large oscillations. You see here I have a large oscillation or over here have large oscillations because the anti-reflection coating fails to work. And so there are some physical limitations, and so that's where the supercomputer comes in, where we really try to optimize now these 60-dimensional structures to kind of vary the whole structure to kill those oscillations inside of the structure. Another approach was to actually use chirped mirror pairs, or one suggestion that also came from ETH group, which actually never really worked, but anyway, that's kind of a nice idea. You grow the mirror on the backside of your substrate. The substrate has a small wedge, so the laser beam comes in, it's reflected on your mirror, comes back, and the residual reflection from our imperfect anti-reflection coating does not interfere with the main laser beam. So that actually gets rid of these oscillations. Why it never really worked is simply you introduce more dispersion into your laser. Every mirror now suddenly has a few hundred microns of extra glass, which is just about how much you can compensate with the mirror itself. So it was kind of not very successful. Another approach was to actually, instead of having one mirror, this is a chirped mirror with air coating, you can think of you have a little bit surface reflection, so that leads to a pre and post pulse. They have a fixed phase relative to each other. I introduce a second mirror, but I add a quarter wave layer of transparent material in the first section, and that leads to pre and post pulses with exactly the opposite spectral phase. If I have two of these two things will interfere with each other, and I can kill these oscillations by actually killing those two pulses. And here is kind of the ultimate 1-octave spanning mirror. It really has high reflectivity from 600 nanometers to 1200 nanometers. The oscillations of each mirror in dispersion is humongous, so the blue and red lines are these large oscillations. But if I combine two of these, I have one bounce on one mirror, on the blue one bounce on the red one. After this double bounce, I'm ending up with the green curve, and so a nice cancellation of those oscillations. And in practice, since you have these 10 nanometer layers, it didn't quite work as well, but it's still significantly better than anything we have had before. And so the oscillations are still pretty small. And we actually did get a full octave of reflectivity, a little bit more. And so this is kind of the laser system I built when these mirrors came to our lab. It took about 3 hours to finish the laser and actually made octave spanning light right away. And it's very small. It fits on a half of or a little bit less than a letter paper size footprint. You have a couple of bounces, and you have to have the same number of bounces on the blue ones as on the red ones. So here I have 2 bounces, here I have 2 bounces. Then on this side I have 2 4 bounces, 2 4 bounces, and output coupler. So once you go through your nonlinear medium, this cancellation effect doesn't work, but as long as you're in the regime where everything is linear, this will work really well. And so this laser has a Fourier limit of about 1.3 optical cycles, that's 3.4 femtoseconds, and you see no more prisms. We added some material to actually fine-tune the dispersion, but this is essentially 1.5 millimeter of volume fluoride. But this allows you to kind of insert a little bit more, especially if the air pressure changes. If it's bad weather, the dispersion of air is so large that this laser will no longer produce an octave. And so this compensates for it. If you have bad weather, well, you insert a little bit more barium fluoride. If you have nice weather, you go either to the beach or you remove some barium fluoride, and the laser works again. So here is kind of a spectrum. You reach an octave, which is important for tomorrow's class. Another thing that's now enabled by those mirror technology, you don't have prisms anymore. Prism sequences are long, so you're looking at something like 2 feet in length. If you want to make a laser that has very high repetition rate, here is one that was done at least 8 millimeter long between these mirrors, and so obviously you can no longer fit prisms in here, but you can have a chirped mirror here to compensate the dispersion of your laser glass. Do you have some questions about dispersion compensation and where to go, or do you have a question?
To do with the AI coaching, how does it demonstrate what's the scalability possibilities with putting now coding like coding in your chirped mirrors?
So this laser produced peak powers of the order of about 7 megawatts inside of the cavity. And
right, okay.
So the peak power is really high because you have, typically you have 10 watt in the laser, but you have only a few femtosecond duration or a few nanosecond pulses. So the peak power is high, and the air cooling itself doesn't necessarily affect the damage. Actually, the damage threshold of a mirror is severely improved by minimizing the electric field on the surface, and obviously on the air cooling that's probably not the case. If I have time, I will talk about the system we built, which produces 3.5 kilowatts of average power and about a half a gigawatt peak power. And there we have severe problems with mirror damage. So it's 1,000 times more than this. If you focus that thing in air, it will just ionize the air. So that's really highly nonlinear optics. But for these, we have not had really damage issue. Once I burned one mirror with the pump laser, but that was more nice. Of course, things have to be very clean. Other questions? Okay, so now we have short pulses. What can we do with them without any application? It's a pretty academic, boring thing. You can write a textbook, nobody's going to read it, and it's all done. So we want to do something with it. And so, of course, we have excellent time resolution because suddenly we have something of the order of a single optical cycle. That's as good as it gets, as we learned in the previous class. With the same color, you can never get anything faster than that. Actually, you can cheat it a little bit because you can actually be phase sensitive, and that's what the lecture will be all about tomorrow. With phase sensitivity, it can actually be much better than a single optical cycle. But nevertheless, time resolution, the way we have seen the horse running or the buffalo with the cool hair effect, you can, of course, do time resolved spectroscopy or so also complex photoassisted chemistry, which I will have no time to talk about. But another thing, which already you kind of pointed out, having a short pulse, even at low power, gives you insanely high peak powers. And actually, on about 2 optical cables, you can build a system that has a peak power about 1,000 times higher than the world nuclear power production. And so I'm talking large numbers here. I'll show you how to do it. Okay, so pump probe measurement, for instance, that's a very simple time-resolved measurement. We have seen I can measure short pulses by actually doing a correlation, or a pump probe measurement goes kind of in a similar way. I have my short pulse, I copied just a small fraction on a beam splitter, maybe a few percent come out here, and the strong pulse is used to excite a sample. So assume this strong pulse does something to the sample. Either it burns it away, or it excites electrons in it, and when you have excited electrons, the reflectivity of the sample might change, or the absorption of the sample might change. Well, a satchel absorber, right? I hit it with a strong pulse. I want to bleach it. Now I want to see how long does it remain in the bleached state. And so that's the job of this small pulse. I send the pulse through my sample with a certain time delay, and if the first strong pulse really bleached the sample, the small pulse will transmit at ease, and I can measure a little bit more average power from this arm. And that's exactly how pump probe works, and that's actually how we measure the recovery time of such a semiconductor satchel absorber sample. I think I don't need to go in detail over it, but so this is kind of something you can do directly in the time domain. I already told you I'm much more passionate about the frequency domain because you can do significantly more stuff there. So I want to leave it pretty much at this, except that we can actually do high average powers. So let's take a 1 watt continuous wave laser. Well, how much power, how much peak power do we have? Well, 1 watt because it's continuous. At any time it emits the same amount of power. Now I take the same amount of power, but I squeeze this energy. So 1 watt means 1 joule per second. Now I take this energy and I squeeze it into a femtosecond pulse. Ooh, then I get a really high peak power. And actually, even if I don't squeeze a whole second, but only 10 nanoseconds, as we did that in the previous laser, 100 megahertz, or around every 3 meters I get a pulse. If these pulses are 5 femtosecond strong, I get already 2 megawatts of peak power. So I have 1 watt, I have 1 watt average power, now I have 2 million watts peak power. So 2 million watts peak power, you remember yesterday's class? We mentioned the Chi-2 process is very inefficient, so we need about 200 watts.
I give you 2 megawatts, so you can imagine whatever you do with that, it will work, probably, or it will vaporize something. And of course you can do much more. You could now, for instance, decrease the number of pulses per second, which automatically increases your peak power. And so that's what people do with, for instance, this kind of chirp pulse amplifiers. They use usually kilohertz or even only 10 hertz of pulses, so 10 pulses a second. You stretch it out in time using some extreme dispersion, so these are gratings. In this arrangement, they cause a huge dispersion, meaning red and blue propagate at very different speeds. So what I get is a very long pulse, which sounds again kind of stupid, but I take the long pulse with low peak power, I send it through an optical amplifier, like the titanium sapphire crystal used inside of the laser. I amplify this long pulse, it's still very long, but I want that low peak power so I don't damage my amplifier. Once I amplified it, I compress it again. Here I don't actually go through any medium, so I'm fine, I'm just reflecting from a grating. And actually for a high energy laser, these gratings are about 1 meter long to have a large spot on it, so I don't vaporize anything. But at the end I come out with a really intense pulse. So here is kind of the history of intense pulse generation. 1960, the first kind of Q-switching mode locking, 65, first mode locking. I get focused intensity. So when you do physics, it's not so much the power that matters, but it's more the intensity. If you take your magnifying glass and you focus the sun, I hope not on a bug, but on something else, well, it gets hot because of the intensity. You had the same power before, but now you made it more intense, so something new happens. Now you can do that with a laser as well, and what you can do is something of the order of 10 to the 25 watts per square centimeter, so that's kind of crazy amount of power. Here is maybe the intensity on the sun ranks about 10 billion times below that, so the sun is a pretty boring object in this respect. And so chirped pulse amplification, which we just saw on the previous slide, is really kind of the key technology to come up with very, very high peak powers. Actually, if you shine this light, say, on a thin metal plate, of course, first of all, you vaporize the metal, but you do more. You start to rip out electrons from the atoms because the electric field is so high that you ionize everything. And the fields here are so high that you actually get electrons accelerated in the electric field of the light to tera-electron volts. So really relativistic physics by simply shining focused laser light onto a piece of metal. Or on a bar again, but bars don't work as well as aluminum, turns out. And NSF doesn't give money for boxes. So here is actually a system, it's called Hercules, of course, nice name, but it's not very large. It's surprisingly small, but the trick is, see, 15 joules. If you have 1 pulse per second at 15 joules, that's a mere 15 watts. I mean, my car battery can deliver more than 15 watts. But the point is, you have 15 joules in 30 femtoseconds, you get half a terawatt peak power. Half a terawatt is 1,000 times more than all the nuclear power plants on the planet together. So it's a lot of power. And then you go and you focus this amount of power into about 1 micron diameter, which is about 10,000 times less than the cross-section of your hair. Imagine you would do that with a AC outlet. Already bad things happen, but now you have billions and billions of times more power. So really interesting physics can come out of it. So kind of the time domain with ultrafast pulses, the really big push right now is in this high energy physics on a tabletop scale. What you could do in a particle accelerator before, you can do now in the lab. A tera-electron volt is big. It's about a 3 kilometer long linear accelerator. This thing happens all within a few microns on your table. That's quite the new regime. Another thing we did is, I told you already, we made a laser that kind of makes some insane power, but by far not so much. But we take the laser, it's about half a gigawatt peak power, we focus it into a gas jet, and in this gas jet we eventually actually rip out the electrons. So the intensity here is about 10 to the 14 watts per square centimeter. Here this is taken with a small picture camera in the video mode, and you see the ionized gas in the laser focus. You see the glow because eventually the electrons will recombine and the gas starts to glow. It's a laser-induced plasma. We talked about Chi 2 and Chi 3 yesterday. We are doing Chi 1 bazillion here because this is an extremely nonlinear process. You have an electron, it leaves the atom, it gets accelerated in your strong electric field from the light. It's an oscillatory wave, so essentially, eventually it will turn back and it will slam back into your ion. And on this trajectory, it can gain a lot of kinetic energy. And all this kinetic energy can be freed in form of light. And so this way we can actually produce very, very short wavelengths of light. If I have time, I will talk about this in the fourth lecture. So this is kind of a way to make attosecond pulses as well. Okay, so we have good time resolution and really high peak powers. I don't know any other experiment that can achieve such high peak powers. Is that all? Well, of course not, otherwise I would have nothing to talk about for the next 2 lectures. And so what we really neglected pretty much is the frequency domain. And I think that's a very good way to stop and answer some questions. And if there are not enough questions, I continue. So please ask some questions. Yeah.
Oh no, I'm sorry, I was doing that. I don't have a question.
So what would you do if you have a petawatt? Any ideas? These are projects you can work on. I mean, these are not very large. It's very different from working for a particle accelerator facility because actually I studied particle physics, but I find these kind of things much cooler because if you are a particle physicist, you're either a super brain, which maybe gives you some interesting theory, that happens 3 times essentially maybe, so the chances are not very high. If you do a tabletop experiment, you can decide what you're doing. If you are working at a large accelerator facility, go for instance to CERN, I believe that thing costs like $20 billion. Well, you better are sure that if you turn that knob, nothing blows up. So you have to go through a whole series of accreditation and make sure you don't screw up anybody else's experiment. But here, these are small-scale experiments, and still really interesting physics can come out of it. That's something to consider for your future careers as well.
I'm just wondering, when you talk about this extremely high power pulses, are you controlling this field? I mean, because I would suppose everything gets vaporized.
Oh, you mean can you control the phase, the electric phase of the...
Just how do you control the field? I mean, the position of it and all that. Because I would suppose anything you throws at its field just vaporized.
Oh yes, so actually for this very high power, the trick is you go very big. So you have very large optics. And then the intensity is low enough not to vaporize anything. But it's not trivial to handle this. Actually, in a particle accelerator facility, I actually do have a picture of something like that. Not particle accelerator facility, but you might be aware of the National Ignition Facility. In California. There we go. So here is an amplifier system. This is the largest freaking laser, as Dr. Ivo would call it, in the world. And actually it fills the whole building by itself. And these tubes are 192 amplifier. And these are large, very large discs of doped glass. And large because then you can keep the intensity low. But a very big problem there is you put so much energy in each individual amplifier that it starts to heat up. It heats up enough that it takes 20 minutes to cool down after a single shot. But this heat leads to a change of refractive index and to all sorts of distortion of your noise transverse mode. And so this has to be corrected afterwards by deformable mirrors. So you have a mirror, it's kind of like a metal membrane, for instance, and behind that metal membrane you have many patches of metal, and by applying DC voltages, the membrane gets kind of electrostatically tuned, and this way you can fix the mode again. So you can undo the mode distortion. And then, of course, you use large optics, and you hit the last focusing mirror when the beam is large, and then you will propagate in space, in free space, actually hit everything in vacuum, otherwise, since ionize and you lose all the light. But all this power that's generated, so you kind of charge up everything for 20 minutes, then you have one shot, and all this light gets focused into something this small. Of course, bad things happen here. And actually, the fields get so hard, so large, that due to the compression of the light force, and also you eject some matter, and the heat is high enough to actually trigger nuclear fusion, which is kind of a hard thing to do. You make a mini nuclear bomb in here, it blows up. You had a question?
Is that power high enough to see nonlinear optical effects in vacuum?
Aha, good question, not yet. I'm not sure, are you aware of any?
Sorry, that's the question.
So nonlinear polarization of vacuum, that's a very good question. So photon-photon scattering, right, you would get it. So can you get fields high enough that you actually get a substantial photon scattering effect? And I think there were some papers about 2 years ago, but I don't believe it. And so polarization of vacuum is rather hard business. It's not impossible. I think we are getting there eventually. I mean, that graph I showed you, the history of high peak powers, it looks like curving down. I'm optimist, so I will just keep going. We need shorter pulses, more power, more funding.
I just have one comment. Concerning the comparison you made between linear accelerators or any type of accelerator and your half-petawatt.
More fluids.
Well, I mean, the power is associated with the sheer number of photons that you're generating in a small period of time, but with a linear accelerator, it's momentum that you're generating. So you have a large amount of momentum, which causes the interaction you require, whereas in your case, it's flooding with lots of photons, actually. They all have the same energy.
Yeah, so
There's small amounts of, not much momentum in each photon. So.
well, you still have the same energy. That means you have, this is tera electron volt for the particles you accelerate.
Yeah.
So you still get tera electron volt electrons, so they have the same momentum as in the LINAC.
In the electrons, yes.
But in the LINAC, you have more average power. Typically, actually CERN consumes about half an atomic power plant, and you get a higher flux.
Yeah.
The flux here is very small, but the energy is comparable to a normal like electron confirm that. But the flux is too small to do experiments like that. And the next step is free electron laser actually. You have a large linear accelerator, you pump in many hundreds of megawatts of average power to create gain. And so you have electrons traveling around your accelerated tube, then they go through an undulator, which is essentially alternating magnetic fields, DC fields. And you know you get Bremsstrahlung, but actually you might not know that you can actually use Bremsstrahlung as an amplification medium. And so this allows you to get insanely high peak powers with that. And so that will probably happen within the next 10 years. When I was in Boston, we started on some proposals to do free electron lasers, and I think in Europe they have some proposals now. That will be the brightest source in the universe. Yeah.
So we create so much, a lot of power in that peak. So how much energy is consumed to actually create that?
So that's actually the beauty of solid-state lasers. Solid-state lasers can be very efficient. They can have efficiencies of, if you are good, maybe 80%. Maybe not quite, but in a system like this, the efficiencies are less, but they are still actually of the order of a few percent most likely. And so since the average power is very small, it's not a big deal. And so I showed you, for instance, this laser that produced 100 femtosecond pulses. This already produced about 100 kilowatt peak power, but it only consumed less than 1 watt total electric power. The trick is really that you kind of use the laser medium to store your small amount of average power, but it stores energy in the excited state. When the short pulse comes through, it takes away a lot of that energy, but only in a short window of time. And so on average, you have very little power, but in this very short instance where you have the laser pulse, the peak power is really high. So the trick here is to have low average power, but very high peak power for a short amount of time. You know, the energy is simply power per time, so if you have constant power, you make time short to get more peak power. And yeah, that's where particle accelerators are very different, since they actually have very large average powers.
Well, since this is a school for material scientists too, you know, in addition to high energy physics, what do you think would be most cool thing you could do for study of materials?
Well, there are actually many applications for material science, and some of them are like low energy electron diffraction to investigate superconductors or pair formation in superconductors. What you need there is usually energies of the order of a few electron volts, which are really hard to produce with a continuous wave excitation. I went to visit a friend in Tokyo 2 weeks ago, and he's working on a picosecond laser system to produce very narrow line vacuum UV radiation to solid state physics. And so they want micro electron volts, a few 10 micro electron volt energy resolution in a lead setup. For solid state physics, of course, a lot of dynamics in semiconductors were investigated using this control technique. You can learn a lot about these. For instance, when you excite electrons in a solid, you can measure their dynamics very well. For instance, electron scattering. This occurs on a very short time scale, typically of the order of a few 10 femtoseconds. So that's where, for instance, time resolution is good. Or in your lab, you do coherent Raman spectroscopy that only works because you can create a phase-coherent broadband spectrum, which you don't do directly in the laser, but by Chi-3 processes. And so coherent Raman is another nice way of doing some investigations on solids. We also are interested in, for instance, growing graphene, single atomic layers of graphite. And we are especially interested in the electron dynamics on those materials. And so you need typically about a gigawatt per square centimeter to really scare the hell out of all the electrons in there at once. And so that's where femtosecond lasers come into play. There are many applications far away from laser science, and we are working very hard to make lasers that can be used by somebody who has really no clue of how to use a laser. So I showed you this very short laser cavity. My goal is to make a femtosecond source that fits in here, so you don't need to know about it at all. For instance, 2-photon microscopy is another application. You want to do microscopy on biological tissue. Biological tissue doesn't like very high average powers because you vaporize stuff. But a very short pulse with high peak power might be okay, for instance, for brain cells and stuff like that. And so there are 2-photon microscopes, but the laser system is usually prohibitive expensive. We are looking at about $100,000. So we want something much cheaper. But it's a big challenge. That's why it's interesting. Whenever you encounter something really difficult, that's probably the problem you want to work on. Easy stuff is boring.
So the commercial tensify lasers currently cost, 120K, 100K, depending on where you buy from, right? So the ones that you could use for, say, 2 photons, 3 photons, fluorescence spectroscopy and biological applications. But where do you think, we could go with, those new approaches? Can those be a lot more affordable?
Oh, yeah. In principle, you know that you could, in principle, build a fiber laser for a few $100. But the problem is it's not mass producible. So what we are trying to do eventually is chip scale lasers, which are mass producible. I mean, how many lasers do you have at home? Are you aware that you have probably about 10 lasers at home? You have a laser in your car, CD player, you have a laser everywhere. I have a laser here, obviously illegal. I didn't know that we can bring green lasers to Australia, but nevertheless. We have many lasers in our daily life. The reason is simply these things cost 20 cents. There is no Blu-ray without blue laser diode. Blue laser diodes didn't exist about 5 years ago. So that's all material science degrees, and I'm very confident that we can do a similar revolution in solid state science. Probably the market will be smaller, that means the costs will be high, but the laser I showed you, the battery operated laser, that was about $5,000, even though it's a single piece, and it could be produced much cheaper than that. And it's already gives you 100 femtosecond pulses. And it's actually, it's a phase stabilized quantum. The most expensive laser we have ever built by ourselves was a high power fiber laser producing about 80 watts of average power, about 10 megawatt peak power at the output. And these things are of the order of $100,000, and their power is 50 kilowatts. But photons are cheap. You can make them. All right, I think.
Want to finish? Okay, great.